So it is a huge pleasure to welcome Professor Nir Davidson today from the Weizmann Institute of Science. Nir has been working in the field of laser cooling and quantum optics, Bose-Einstein condensation, and we came across Nir's work with some seminal works that he did on coupled lasers, which is also the topic of his talk today. So currently, Nir is the Peter and Carola Kleeman Professor of Optical Sciences in the Department of Physics of Complex Systems at the Weizmann Institute. And it is with huge pleasure that I give you the floor, Nir. Thank you for coming today.
Okay, thank you very much, Pavlos, and thank everyone for attending. And I do apologize again for not being able to show myself. And I wish you a good start of your new academic year, because I understood this is like the very first seminar of this year. So with that responsibility, I will try to tell you about our work with coupled lasers. So let's just put, okay, here are the coupled lasers. And what I want to do, I want to give you an overview. I know some of the people, Pavlos in particular, have already heard me several times. And there is a little bit of material that I repeat, and more importantly, some of the jokes I'm going to repeat. So if you heard them already, I apologize. Now, and please, if at any point somebody wants to ask, I think it's better to unmute yourself and just ask loudly, because I'm not sure I will follow the messages. Okay.
Thank you.
So the title of the talk, and I'm from the Weizmann Institute, and I'll show my students and postdoc, which of course did all the work, in the very, very end. So I want to tell you how to simulate spins and solve computational problems with coupled lasers. And I want to start by giving you a few lines about what are coupled lasers and why they are interesting. So if you look on the bottom of the screen, on the left part, where my mouse is now, you can see 1,500 little spots. Each one of them is a laser coming out of the screen towards you. And as you probably know, there is a big difference whether there is or there is not a phase relation between the lasers. So if the lasers are uncoupled, they are independent, then what I have to do when I look on the diffraction pattern is to add the intensity of each diffraction pattern. Now, if you look on this middle spot, this is called far field in optics. It just means taking the Fourier transform of the field or putting a lens and going to the focus. So you see this big blob is actually the Fourier transform or the diffraction pattern of a single laser. As you know, in optics, when you are small, your diffraction pattern is big. This is the Fourier relation. So each one of these lasers is small, is about 100 micron, and therefore the diffraction pattern is big. Because we have 1,500 lasers, we have to take 1,500 such diffraction patterns, but because we add them in intensity, they are just identical. So we actually, what you see here is actually the sum of the 1,500 diffraction patterns, which are incoherent with each other, coming from each one of the lasers. If we couple the laser, as I will show you during the talk, and now they are all phase coherent, and let's assume they all have the same phase, so they are coherent with the same phase. In the language of spins, we would say this is a ferromagnetic configuration. Then all these fields interfere, and what you see here these very sharp diffraction peaks. Sometimes they are called Bragg peaks, borrowing from condensed matter. And the brightness that you see here in the central peak is actually, you have to sum 1,500 fields and then take the square. So this is 1,500 times more bright than the center of this field. And also the area here is 1,500 times smaller than this area. So you have this quantitative relation between the sharpness of the diffraction peak and the coherence function of the array. In this particular case, all the array is coherent, so all the lasers are phase locked, so the size of this diffraction peak is actually the Fourier transform of the entire array size. And because the area of the array is much larger than the area of the laser, you get this very sharp diffraction pattern, and you see these additional diffraction spots, you would call them the first order diffraction spots, coming from the periodicity of the grating. Okay, so this is phase locking. It's well known for many, many years in the laser community, and I think also in polaritons, you can have many polaritons phase lock, and this would be the signature, looking on the diffraction pattern and seeing the interference. This already brings you one motivation why you want to couple laser and why you want to phase lock, and this would be the sharpness of this peak. Even though you have the same energy in this picture and in this energy, and in this picture, the energy here is concentrated many orders of magnitude more than this one, and this is useful for many applications. I'm showing you several of them where you don't just want a lot of energy, but you want to concentrate this energy on a small spot or go to a large distance. I'm showing you another application which my students like very much. If you want to cut your pizza with the laser, you also want to focus it to a nice point. And this is something that our group worked for actually quite a lot of years, and in the last decade, as Pavlos mentioned, we are now motivated into a different question or different goal, and this is the relation between the coupled lasers, or the phase of each laser, and spins, in particular XY spins. So just looking on this picture, you can see that if each laser is characterized by a phase, which is a number between 0 and 2 pi, let's say in this particular configuration it's 0 pi, 0 pi, then you can plot this number as a little arrow, and you can call this arrow a spin. And in this picture, it would mean that this phase configuration would correspond to this antiferromagnetic alignment of a spin XY spin system. Now, is this just a picture or an analogy? Actually, it's not. There's a much more quantitative relation which motivates our work, and I will discuss in detail in the upcoming slides. Okay, so we shifted from drilling holes or shooting down rockets into trying to simulate spins and solve the computational problems. Of course, we are not the only one. This is now an emerging field, and it even has a name. It's called coherent computing. Coherent because we are relying on the phases and the coherence between the phase, and computing because the mapping into the spins will allow us to solve computational problem. And the general idea is capturing this illustrative figure, which is taken from the group of Yamamoto, which I think were one of the pioneers of this field, as I'm sure many of you know. And the idea is that you have many physical parameters. In our case, this would be the laser phase, and they correspond to not to the energy of the system, as sometimes done in a Hamiltonian system, but actually to the loss. And coupled lasers know to minimize the loss by mode competition, and this is a very effective process. Actually, it's exponentially effective, which is good to have an exponential resource when you come to a hard computational problem. It doesn't mean that it's enough, but it's at least useful. And the idea is that the lasers will dissipate themselves by this dissipative coupling between them, which I will discuss in a moment, into lower and lower loss states. And because computational problem has this complex landscape, which has many local minima, it's not clear that the lasers will be able to find the global minima. This is one of the things that we have to study. And also, I want to remind you that actually this picture is a simplification because we actually are living in a 1500 dimensional Hilbert space, where this is just one laser phase, and we have another 1500 lasers building this Hilbert space. So this is really a complex landscape, and not getting stuck in local minima and finding the global minima is a big challenge, not just for our group, but for many other groups. Okay? And this is a recent example, again, from the group originally for Yamamoto. You see he's not here anymore. He went back to Stanford to look for new ideas. But this idea was really performed amazingly well by a company, by a Japanese company. This is called an IZ machine and not an XY machine, because they use degenerate optical parametric oscillators, which because of their symmetry have only 0 and pi phase, so they can map to Ising spins, which actually has some advantages over XY spins. And you can see they realize in a very different way, not in the spatial, but in the temporal domain, a rather large system, which now you can even run on the cloud, so they say. And this is part of a general trend of what is sometimes called annealing machine, sometimes annealing, sometimes quantum annealing, which comes at a large variety of systems. I just named a few of them, even you see you are there in the polariton. But starting with D-Wave, which probably attracted more attention in the recent years. Here are the lasers. With Weizmann, Light Solver is a spin-off company of our group, and several other groups are doing coupled lasers. OPOs, as I mentioned, to map the Ising spins are in Stanford, NTT, and several others. By the way, all these places are actually ex-Yamamoto students. So you see this work, even if he didn't generate a good solver, he generated a lot of academic positions for the people writing the paper. So it's already nice. And a large variety, photons, electrons, and would you believe even micro droplets can be used to compute, and of course called atoms. And there are many others. And I'm going to talk about coupled lasers, and I just want to mention this company. This is not a propaganda for the company. It's more like an excuse. So there is sort of a division of work between our academic group and the company. The company, of course, is supposed in the end to make money. We don't make money. And the company, to make money, you need customers. And the customers comes with their problem. And their problem means that you have to program the connectivity between the lasers, which will be mapped to the connectivity between the spins. This is sometimes called vector matrix. Imagine a long vector of spins, and then arbitrary coupling between them would be represented by a matrix. I just want to remind you that vector matrix is a very common problem in optics and was dealt a lot since the 80s, but most of these solutions are extremely inefficient, and you cannot incorporate them inside all optical system as we do. So that's what the company is doing, which gives our academic group the excuse not to do it. We don't have any customers. So all the results I will show you are physically motivated. And physics is usually not arbitrary. And I will show you things like nearest neighbor connectivity, next nearest neighbor connectivity, all-to-all connectivity, spin glass connectivity, random connectivity. You see, none of these is really solving a traveling agent problem of such. This I leave to the company. So if you ask me questions, of course, I could tell you a little bit about these vector matrix ideas, but at the moment, this talk will be concentrating on physical problems, okay, which is just a small section of what you can solve with these spin Hamiltonians. So what is the outline? So I'll show you the mapping to spins. I already tell you that I'll show you that it's imperfect, incorrect, and even inconsistent, but still it's useful. And you see all sorts of interesting spin systems like triangular, Kagome, quasi-periodic. If I have time, I will show you a different class of problems, which are not discrete in that sense, but are continuous. This is, for example, a mode of our laser. We call it the Einstein mode, and you can guess why. And this is actually composed of 10,000 individual pixels. So we have a lot of more modes than pixels. And we can play the games in the continuous language where we don't talk about spins, but we talk about continuous fields. I'm not sure I will have time for that. So let's start. And I want to start at the very basic level, just so we are all in set, and just to remind all of us what we mean when we say phase locking. So we have two lasers. And these two lasers, if they interfere on the screen, we do not see interference, for instance, in general. And the reason that each laser has a phase which is fluctuating quite rapidly, actually in our case, about 1 million times per second. So if your camera averages on a longer time scale than 1 part per million of a second, you average these fluctuating fringes. Now, when you couple the laser, they are still fluctuating. So each laser has a fluctuating phase, still fluctuates 1 million times per second, but the fluctuation is correlated, okay? So the phase difference between the laser is now constant, which means that these fringes will survive the integration time of the camera. Actually, they can survive the week. We can put them on the Sunday and come on the end of the week, and they don't move at all. Our system is quite stable. Okay, so this is what I mean when I say phase locking. And I already want to show you the first way we couple the laser, which is actually quite similar to what was done in polaritonics. So I think it's like, just put them close together and something will happen because the fields will overlap. So I'm already using this opportunity to show you that we don't really take two independent lasers, but we actually take a common laser cavity. And for this talk, it's enough to know that to build a laser, you need two mirrors. One of them, of course, is partly reflecting to let the light go out, and then the light goes back and forth, and you need some gain medium, which in our case is YAG for 1 micron. And in order to define the two lasers, I just defined two regions in the laser. I put a mask with 2 holes, and here are the 2 fields. And now simply by propagating back and forth in the mirror, light diffracts, we know that. And after it comes back, you see it spreads a little bit. So now I have these 2 Gaussian modes, and you see that they are overlapping. And because they're overlapping, they are coupled. Namely, light comes out of this hole, may leak into the other hole, so we have coupling. What is the strength of the coupling? Is just the overlap between the modes, right? Let's go to the second. And the overlap between the modes, if each mode is indeed a Gaussian, then the overlap between two Gaussians is a Gaussian in the distance between them. So imagine if we didn't have 2 holes, but like 1,000 holes, as I showed you before, we would call this nearest neighbor coupling. Because the coupling to the next nearest neighbor, imagine there's a hole here, would be Gaussianly or exponentially smaller than that. So in this first example, we are implementing short-range coupling, or if you want, nearest neighbor coupling. The other important point, which I hinted on before, that this coupling is actually dissipative. And if you write it by two matrix, you will see that the coupling is actually imaginary rather than being real. And you would see that the matrix, when you diagonalize it, instead of getting real values like Hermitian matrices, you actually get imaginary values. So they are not energies or frequency, but they are rather loss. And this is the unique aspect of coupling between lasers or oscillators in general, which I think we share to a large extent with polaritonics. So it's not a bug, it's a feature. The fact that our eigenvalues are imaginary allows us this dissipation into a solution. And just to give you a flavor of that, imagine if I start with a superposition of the two eigenvalues, eigenstates of this 2 by 2 matrix. How will they propagate with time? In unitary systems, eigenstates propagate as e to the I omega t. That's what they do, and omega is real. In our case, because the eigenvalue is imaginary, so I have e to the I multiply imaginary value, so I have e to the minus lambda t. I have exponential decay with the magnitude of the eigenvalue. And if I have two different eigenvalues, high loss and low loss, what will happen to a system starting in a combination? It will purify itself, right? Because all the eigen, and this is the same if I have 1,000 eigenmodes. All the 1,000 eigenmodes will decay exponentially, and the one with the minimal amount of loss will decay slowest. So after some time, it will be exponentially stronger than the other one, and the system will purify into a pure state. Which pure state? The minimal loss solution. Of course, in laser, we also have gain to compensate for the exponential loss, so we can stay with a finite system, okay? So this is the general idea, and dissipation here is the crucial part of all the business. And I've written it here. So now let's use this idea, this concept of minimal loss, and let's try together, you cannot see me, but let's try together to guess what will be the phase that the laser will choose to phase lock in this case. And I know in polaritonics you have all these issues, how to control the phase between the coupling, but here it's going to be very easy because we look on these two fields, the red one and the green one. Of course, they are the same wavelengths. And here they overlap, so in the interfere, and you see this is not a hole, this is a block. So what would minimize the loss? If the interference between them will be such that I have here 0, namely destructive. So you see this corresponds to a pi phase between them. And here I'm illustrating here, you see now they interfere and you get 0 here. So what is phase locking will be at pi phase difference or antiferromagnetic between these two neighbors in order to minimize the loss. And then I will see the interference ranges from which I can measure that indeed it's pi. So this is the basic idea, but of course we don't put a mask with 2 holes, we put this mask with 1,500 holes, which we actually drill, okay? And that generates a problem, and the problem is that the holes are so close, so the coupling will be always and too strong. And what we want is at least to start with an uncoupled system, as I showed you in the beginning, and then to introduce the coupling in a controlled way. In order to avoid this coupling, to avoid the diffraction, what we do, we actually put a 4F telescope inside the cavity. Okay, you see this is 2 lenses, and starting from this field where the mask is, which we call the near field, we go F, 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 F. It's called 4F in optics. So the field from here is imaged on the other side, as you can see here. And then we go back another 4F, so it's entirely 8F telescope, which inverts it again. So you see, this is a very strange cavity. If you have never seen it, you should be a little bit surprised that it exists. It's called the degenerate cavity. And the reason it's called the degenerate cavity that any field distribution is imaged upon itself. So the modes of this cavity are all degenerate. And you can build from this semi-infinite basis. Actually, we counted something like 500,000 modes in a recent work that we did. This is a lot of degrees of freedom that we have, and they are all degenerate to a large extent. They are so much degenerate that in spite of mode competition that I told you before, many of them survive. So we can typically lace with hundreds of thousands of modes. And this degeneracy between the modes ensures that we can use all these degrees of freedom. So basically, this is our resource. And then, of course, we will introduce the loss as at will in order to select the solutions that we want. But this is on top of this highly degenerate system. And indeed, when we do that, this is the picture I showed you in the beginning. The lasers are not coupled. If you want the light coming out of each one of these holes that we now call laser is imaged back exactly to that hole. And this only happens when the student aligns the system very well, because you see they are quite small. And then we get this diffraction pattern of uncoupled lasers, of incoherent lasers. How do we introduce coupling? I already told you before, diffraction will give us coupling. So now we have to take this mirror and just move it a little bit, maybe a centimeter. This is about a meter. And you see that the diffraction pattern now is suddenly composed of these very, very sharp diffraction peaks, or Bragg peaks, if you want. And I also remind you that the sharpness of this peak tells us the coherence of the array. And in particular, if the size of these peaks is the diffraction limit or the Fourier transform of the entire array size, we know that the entire array is coherent. All the 1500 lasers are phase locked. And now you can see these diffraction patterns are not in the center as before, but they're actually on the edges of this Brillouin zone of this square lattice, indicating that we have this 0 pi configuration as we expected from the previous slide. Okay? So now each neighboring laser has a pi phase difference, and the distribution is 0 pi among all the lasers. It turns out that if I now take this mirror and I move it a little bit more away, let's do it, I get this positive coupling. So again, this is the picture I showed you in the beginning, and now the phase between all the lasers, and in particular the neighbors, is 0, 0, 0, 0. So here the coupling is positive, here the coupling is negative. In both cases, it's real. And you could ask what happened to the argument of 0 pi before. So for the experts, it doesn't matter so much. I can tell you that you can look on another point of view, and the other point of view to calculate the coupling is to ask, what is the field the laser returns to itself, going back and forth? And what is the field that the laser gets from his neighbor, that goes here, spreads a little bit, hits the mirror, and come back? And I have to calculate the length difference between going in a straight line and going in triangular line. And if this phase difference is pi, I have negative coupling, pi phase between the two fields. And if it's 2 pi, which is like 0, I have in-phase coupling. And the condition to get pi or 2 pi difference, is, if you probably remember from high school, is to be either at half the Talbot distance or the full Talbot distance. So the Talbot distance, or the Talbot effect, if you remember, is exactly such that the phase difference between going diagonal between neighbors or going and back to yourself is exactly 2 pi. This is Talbot, and this is what we get here. So we can control the phase actually continuously. Before it was pi, now it's 2 pi, but now we can put this mirror in any intermediate position that we want. Let's put it here. And now if you calculate the difference in distances, you will get in any phase that you want. So now the coupling is complex. It's not necessarily positive or negative, real, or what we called before purely dissipative, but now it has this dispersive term, which is another degree of freedom that we can use, and I will show it to you towards the end when we discuss artificial magnetic fields and topology, these kinds of things. If you want to simulate spins, to do a spin simulator with artificial gauge fields, you will need this complex coupling. Okay, so this is a rich system. Another tool that I want to show you is I chose the negative coupling, and I remind you that when you look on this diffraction pattern, I told you that it's 0 pi, 0 pi. And actually, I could do that more formally by doing some kind of a phase reconstruction. Look on the far field, I measure the near field, I could run a Gershbeck-Saxton model, and I could find out what are the phases exactly, and we did that. But just to be sure, we also want to measure them. And we want to know what is the phase of each laser in the array, which seems like a difficult problem, but actually it's not. So what we do is the following. We take all the lasers, this is just part of the 1500 lasers, and we image them twice. First, we image them with a 4F telescope outside the cavity. And second, we take one of them, this one, we expand it So it becomes really large, and it overlaps all of them, and we interfere them. So now if you look and you see all these diffraction fringes, and you can look on a magnified version here, these diffraction fringes are the interference between this selected laser, and we could select another one, of course, and each one of the other lasers. So in a single picture, we have all the information of the mutual coherence between one laser and all the rest. You know, coherence is a four-dimensional function, so we don't see all the four dimensions of the coherence function, but at least for this particular laser, we see all of them, and if the system is invariant, this is enough. So what do we learn from these fringes? Of course, the fringes has a certain contrast, which actually maps to the amount of coherence between the two lasers. Are they perfectly coherent, or are they only partially coherent? This will be determined by the contrast of the fringes, and the position of the fringe tells you what is the phase. So all this information for all the lasers we get from a single image, which we can then change. And then if you go to MATLAB, there's a very simple trick. You do Fourier, you put a mask, you come back, and already MATLAB shows you the coherence, the full coherence function, which I'm showing you here. So what you see here is not the picture of the laser, of the field, but it's actually the mutual coherence between this selected laser and every other laser, where the color represents the phase, and the intensity represents not the field intensity, but the amount of coherence. And what you can see here, that the coherence is indeed drops slowly towards the edges, but it still exists all the way to the edges. So indeed, all these lasers are phase coherent, because you see the coherence, and you see it by the color code that it's indeed 0 pi, 0 pi. So it's a direct measurement of the phases of all the lasers, which is one of the cool things that you can do with optics. So optics is really good for measuring things. Okay, so I come back to this question: what is the relation between the phase of the lasers and these XY spins? Okay, and in order to answer that, I want first to make a simplification, and the simplification I want to make is to look on each laser, which is a rather complicated creature. You know, lasers have many internal degrees of freedom. They can have multi-frequencies, they can have phase, they can have internal structure, multimode, like polaritons, of course. And I'm going to freeze all of them. Also the intensity. I'm going to assume that the intensity of all the lasers is the same. And I will be left only with a single Gaussian mode, fixed intensity, with a certain phase, which is again a number between 0 and 2 pi, which is the arrow that I'm drawing here. Okay? Freeze all the degrees of freedom. And then what do I get? Is there any kind of mapping? What is the relation? So these classical XY spins are represented by Hamiltonian, which I'm writing here, of course, with some connectivities. It's, by the way, it's the classical XY Hamiltonian. Okay? So I'm not talking on any quantum effect today. If you ask me in the end, I can comment a little bit about quantum. But remember that classical Hamiltonians are still hard to solve. Now, next, I want to describe the system of coupled lasers. Usually, I would need 3 equations for each laser, so 3n equations. But because I froze the intensity, and freezing the intensity also freezes the gain doesn't care about the phase, I'm only left with a single equation for every laser. And this single equation looks like that. It's an equation for the dynamics of the phase of laser I, and you see it depends on the phase of all the other lasers that are coupled to it with the coupling coefficient, Kij, which I wrote similarly to here. And this actually is a well-known model, which is called Kuramoto model. I'm sure many of you know about it. It's a general model to describe coupled oscillators, like birds singing in the forest, people clapping their hands. We find that we can exactly get it from the coupled laser equation. So it describes our system under this assumption that all the additional degrees of freedom are frozen. And now comes the punchline. And under this assumption, one can show mathematically in 3 lines, even I can do it, that the most stable state, or the minimal fixed point of this Kuramoto model, which is a highly dissipative model, is identical to the ground state of the classical XY Hamiltonian. Okay? So I'll say it again. Under these assumptions, we have an exact mathematical relation between the most stable fixed point of the Kuramoto, the minimal loss solution, if you want, of the laser, and the ground state of the XY Hamiltonian. And based on this mapping, you could now tell the following story. The laser will find the minimal loss state. Maybe it will get stuck in some local minima. But if it does, this corresponds mathematically to the Kuramoto stable fixed point under this assumption. And it's already well known that the Kuramoto stable fixed point is identical, as I say here, to the ground state of the XY Hamiltonian with the same couplings. Again, this is a Hermitian system. It has minimal energy. This is a highly dissipative system. It has minimal loss, but the state is the same. Okay, with this I, if you want. And this little arrow that goes outside the slide signifies that now, if you know how to measure ground state of XY, and you know how to realize an arbitrary connectivity function, this vector matrix that I'm not doing, but the company is doing, then you can map to a very large variety of mathematical problems. Not as large as the Ising, but quite large. And these problems are mapped to each other, so you can do a lot of stuff. Okay, so this is the story. Is this story correct, as this question mark indicate? And the answer in general, no. So which of these arrows is breaking? Here I'm telling you the answer. Maybe more than one, but at least this one is broken, and we have a recent paper on that. I don't have time to go into the details, but I just want to say that when you freeze degree of freedom, you can always say, okay, in some cases it's correct, in some cases it's not correct, and I'll show you in a moment cases where it's less correct or more correct. But more importantly, this is not just not always correct, this is inconsistent. And what do I mean by inconsistent? I mean that freezing the degree of freedom of intensity of the laser, which is of course necessary. Imagine lasers with different intensity, spins by definition all have the same intensity. By the way, I found there's one paper written by actually an Israeli scientist. What happens to the XY model if the spins are don't have the same lengths? But this is just one paper, and all the rest of the work on XY spins assume that all these arrows have the same lengths. And this is the mapping that we want. But it cannot be done. And the reason it cannot be done is inherent. It's not a problem. It's not that we make bad lasers. Even if the lasers are strictly identical, they have the same loss, they have the same gain, the connectivity will make them non-uniform. And as a simple example, let me show you these 5 lasers coupled with nearest neighbor negative coupling. We call it a house. You can see why. And now think, this is, by the way, what the XY does. So the XY, you know, what it likes to, the XY would do on a square, it would do 0 pi, 0 pi. So the arrows would be like 0 pi, 0 pi. But here it has to be 0 plus 120 minus 120, as you probably know. So it has to compromise a little bit. So this is the minimal energy solution of the XY. What will the lasers do? This is what the lasers will do. If you're close to threshold, which for technical reasons is the place where the solvers should work best, this laser will shut down. If you're not close to threshold, it will not shut down, but it will be weaker than the others. Why is it weaker than the other? Because you see that all these lasers are consistent. With negative coupling, this laser gets the field from the others in phase. They look out of phase, but the coupling is out of phase, so when you multiply, you get in phase. So if you want, instead of saying the minimal loss, you could say the maximal positive interference, which is of course the same, because energy has to be conserved. So ensuring this positive interference is another way to think about the minimal loss solution. This laser is less happy because it cannot get signals in phase, because in best this will be 120 degrees from each other. So you see, even though it's identical, it becomes weaker, and close to threshold, it shuts down completely. So the minimal loss solution of lasers, which is this non-linear problem, including the gain of the lasers, cannot be mapped to the minimal energy solution of the XY exactly because of this sort of annoying intensity. What happens if we force the intensities to be the same? We can do that with feedback. We actually can control the intensity of each laser. I'll show you in a moment. So we actually did that in this publication. This is the measurement. And what you see here is the difference between, I'm sorry, it's a little bit messy, but it's the difference between the phases as we measure for the laser and the phases for the ground state of the XY. So you want to see 0. 0 is success. And here is 0. And 0 is obtained when the spread of intensity between the laser goes to 0 by force. So instead of keeping the lasers identical, we play with the gain and the loss of each laser until they get the same intensity, and then the mapping becomes, let's call it exact. Okay? So did we solve the problem? You could say, yes, you start with a network, you see the intensities are not the same, you do some feedback, you make them the same, and now the mapping is exact. But actually, what this tells you is that this procedure of making the intensity identical must be hard. Actually, NP-hard, for NP-hard problem. So think about it for a moment. The lasers basically solve an easy problem because they found the ground state of some matrix, real, imaginary, but it's still an easy problem. And you want to map it to a hard problem, which is in general the ground state of the XY Hamiltonian with arbitrary connectivity. So this mapping cannot be easy. So we are not allowed to invent a method. If we would, you should doubt us. This is just a taste, and there's a lot of work. Other people, Natasha Perloff and Yamamoto himself. In the beginning, people tried to sort of hide it under the table, but now I think many people realize this mapping between coupled oscillators and the XY inherently cannot be consistent. It's only an approximation, but still it's interesting approximation, and it's a good starting point, as I hope to show you. If I still will have time, I'm sort of going a little bit slow. So saying all that, let me show you several examples where the mapping is actually correct because the system is uniform. Okay? So I already showed you the square lattice, and now I'm taking the triangular lattice, and I actually already told you that if you take a single triangle and you try with negative nearest neighbor coupling, so the coupling is negative, they want to be pi, and it's only the nearest neighbor. So the next nearest neighbor is exponentially smaller. So, but of course, on a triangle, you cannot have 0 pi. So what they find is 0, minus 120, plus 120. This is a little vortex. And actually, there's another solution, which you would call anti-vortex. So instead of 0 plus minus, you'll have 0 minus plus. Okay? So you have two solutions, and the ground state is 2 degenerate. And if I go, for example, to this laser, it has to be 0, because this is minus and this is plus, so this is plus 0, this has to be minus. So you see, I can construct a global ground state for all the lasers, and I still only have 2 degeneracy. And what the laser does, it finds a solution. You can ask me, is it the right solution? I'll show you in a moment that it is. And these diffraction pots, the fact that they're again sharp, tells you that you have this global coherence in the system. Which solution did he find? The first, the staggered vortex or the staggered anti-vortex, actually he found both. And what you see, these 6 diffraction pots, actually 3 of them correspond to the vortex lattice, and the other 3 correspond to the counter anti-vortex lattice. So the two solutions coexist. You could ask me, how? Is it fluctuating in time between them? Do you have different domains, like the top one is the vortex, the bottom one is anti-vortex? Then you would have a defect, and the peaks would be less sharp. So I'll tell you in a moment, where do we encode these many solutions? It comes in the different frequencies of the laser. But again, we have 2 solutions. So we have 2 degenerate ground state. And this is success. He found both of them. The next problem we give him is these kagome lattices. So what is kagome? This nice Japanese weaving of baskets. And if you look, it's really the triangular lattice, or an hexagonal lattice that we've seen before, with a quarter of the lasers removed. This one and this one are removed. So we still have triangles, but now these triangles touch each other only at the corner. And this has a significant difference on the degeneracy of the ground state, and let me convince you for that. So if I try to construct a ground state of the XY Hamiltonian, that's what we aim for. On a single lattice, I again have these 2 degenerate solutions, 0 plus minus, namely plus 120 minus 120, and the opposite one. So 2 degeneracy on the first lattice. Now when I go to the second lattice, and under the assumption of only nearest neighbor, I have another 2 degeneracy. This can be a vortex, and this is an anti-vortex, or vice versa. So already 4 degenerate solution. So all in all, on this lattice containing about 500 triangles, we have 2 to the power of 500 degenerate ground state. This is a very large number. And this is a very strange system if you think about it, having a finite entropy at 0 temperature because of this degeneracy. For example, the third law of thermodynamics will break for such a system. That's what makes it interesting. It turns out that quantum people are interested in this kind of systems because the classical solution is sort of fragile, and this leads to emergence of highly entangled quantum states. I'm sure some of you are experts more than me on that. So you see, we asked our solver, our XY solver, to find a solution, and we gave it 2 to the power of 500. A problem is 2 to the power of 500 solutions. So it should be quite easy, but actually it's not, and this is actually called frustration. The solver sort of is frustrated, doesn't know what to solve, and what it does, it finds sort of a mixture of the solution which has this strange shape. Okay? Does it make sense? Is it the correct solution? So you could calculate and try to average over this solution. It's actually not so easy. We did it, but fortunately, this is, as I said, an interesting problem. It was already solved numerically before by these two great people, Mosner and Choker. They are like the big names in geometric frustration. And this is the diffraction pattern, or they called it the structure factor because they worked with a magnet. This is like supposed to be an approximation for the shape of a magnet with antiferromagnetic coupling, which has a lot of anomalies. For example, it cannot produce long-range order even far below the Curie temperature, just because of these effects. And as you could see, our solver actually couldn't find long-range order, but could find exactly what the theories predicted, including details. You see this little thing, it's called the bow tie, and it reflects some residual correlations coming from the need to close long-term trajectories. And we see these bow ties. So we could do quite well in this rather complicated situation, but we could do more because I remind you, we don't have real spins. We just have lasers which simulate spins. So for example, for us, it's very easy to introduce next nearest neighbor interaction. Just by moving the mirror just a little bit more, so the Gaussian will overlap with the next nearest neighbor. And when we do that, even put just a little bit of, let's say 1% of next nearest neighbor, this is the diffraction pattern we get. We remove the frustration, and if you look on this picture, you immediately see that the degeneracy is removed when you include, for example, interaction between these two next nearest neighbor. So now if you choose here a vortex, this already will remove the degeneracy between a vortex and an anti-vortex, regardless if it's positive or negative. Okay? And this solution, again, you have to believe it, it's the correct one, but at least you can see now we are back to a unique solution by introducing next nearest interaction, which is hard or impossible to do with real spins. So there is an advantage to use an artificial optical system to simulate spins because of its flexibility, not just the design of the coupling, but also the range of the coupling. Maybe I'll skip this slide because it sort of repeats what I said. It's calculating the coherence under this case. And let me show you yet another type of coupling that we use. And this time it's going to be all-to-all, or if you want long-range coupling. So here's again our laser. These are the two mirrors, the gain medium, the 4F telescope. And now in this plane, which is actually the Fourier plane of the lasers, we put a mask. And in the mask, we put a hole, which is a delta function. In optics, delta function is the diffraction limit of the entire array. Okay? So now, let's try to guess all together what will happen, because now we are experts on this minimal loss criteria. So the phase of the laser should be such that the loss caused by this tiny aperture would be minimized. And of course, the answer is they will all be in phase. Because if they are all in phase, as you can see here, this is the diffraction pattern that you get for triangular lattice, and you get these very sharp peaks, which goes through your peak, and this is the minimal loss. Alternatively, I'm skipping the order, you could ask what is the coupling function, and this is a bit technical. So what we do, we multiply the Fourier of this field by an aperture, and if you remember your lessons in undergraduate, to multiply the Fourier is to do convolution with the Fourier of the mask. So the coupling function, because I'm doing convolution, is the Fourier of this mask. And what is the Fourier of a delta function? It's a very wide field. If you want, you think of the photon coming from one of these lasers, going through this delta function pinhole. It's well defined in position, so it's completely undefined in momentum, or in optics it's the angle, so it forgot where it came from. And when it goes back to the laser array, it actually spreads over the entire system, which is what you see here. So we have all-to-all coupling. And indeed, all-to-all coupling, as you probably know, is very good for phase locking, much better than nearest neighbor, because all the lasers can interact together with the phase. And this is indeed our best result so far. So remember, if you calculate the area here divided by the original area, or if you want the distance to the edge of the Brillouin zone, this actually gives you a quantitative measurement how many lasers are phase locked, and here we have more than 5,000. Okay. Once we have this system, we can play games, and this is the first nice thing that we did. You see, we opened this aperture a little bit, and remember that the coupling function is the Fourier of this open aperture. This is the Fourier of an open aperture is this function, which is called sinc for square and jinc for a circle. And you see this is a funny function because it has two properties. First, it decays, but slowly, as 1 over the distance, 1 or 2, depends on the dimension. So it's still long range. And second, it oscillates, and the oscillation is the Fourier of the radius of the aperture. So by choosing the radius of the aperture to be incommensurate with the Fourier of the distance between the laser, we could achieve, for example, this incommensurate oscillation of the sign of the coupling. So the coupling would be positive, negative, positive, negative. And if this is, say, the golden ratio, square root of 5 plus 1 divided by 2, it's an irrational fraction. You could approximate the coupling function to be random. It's not really random, but you could approximate it to be random. And using this very simple scheme, we can implement random in sign, positive, negative, long range coupling between thousands of spins, which is actually a spin glass. So the simple spin glass model have this frustration coming from the random sign of the interaction. So we have, again, highly frustrated, very complex landscape, which the system has to deal with. And this is now something we're working very hard on. Of course, it became somewhat popular in the last year because of the Nobel Prize to Giorgio Parisi. But there are still many, if the Nobel Prize comes, some people say, let's go to another field. But it turns out Parisi was so unique that even after giving him the Nobel, there are still many open questions in this field of spin glasses that we are now addressing. And if you ask me later, I can give you an example. Sometimes we don't like this, spin glass. They are nice to play with, but sometimes you want something simpler, and you would like a coupling function that doesn't oscillate. And I remind you that this coupling function is just a Fourier of what we put here. So which function can you put here that the Fourier will not oscillate? It turns out that just one function whose Fourier never oscillates. You know what it is? It's a Gaussian. So what we put here now in the far field of the lasers, you put a Gaussian mask that we buy from Torlaps. And the coupling function is just a Fourier transform of the Gaussian mask. And in particular, it never changes sign. And indeed, when we implement it for very different parameters, we get either good phase locking or bad phase locking, depending if it's a small Gaussian or a big Gaussian. You see, by taking a small Gaussian or a big Gaussian, we can take short range or long range, but we always get this in phase. And we could even take this random array of lasers. And let me tell you a secret. The way we made it is we tried to make a quasi-crystal by drilling 1,000 holes, and then the person drilling the holes got confused, so we decided, okay, let's do random. And I'll show you in a moment that this made us really tired from drilling holes, and we found another solution. So in this random array, still we could get this in-phase coupling, and if you look now on the diffraction pattern, you see this in-phase, and you see this ring, which you should associate with liquids if you know how the structure factor of liquids look like. So you can say this is a liquid phase lock laser array if you want, just for fun. It's not useful. Pavlos, I see 57 minutes. I don't know when exactly you started. Please tell me when I have to stop.
Yes. Please carry on. This is a very interesting material that you're presenting here. I will let you know. Please carry on.
Okay, but shout when I'm really, too much. So going back to this tiny aperture that we put in the far field and locked many lasers, this was not so easy because you have to align everything very carefully into this very tiny aperture. So the student was a little bit lazy. And then we said, what if we let the laser drill the aperture for himself? So instead of putting here an aperture, we put a piece of plastic, which is called saturable absorber. A saturable absorber is a material, a nonlinear material, which becomes more transparent when higher intensity hits it. So it sort of generates a temporary hole. Sometimes it's more than temporary if you burn it, but we try to be careful. So it's only having a transmission hole where the high intensity happens. And then, because now, again, you're experts in this minimal loss idea, we said the following, maybe. And by the way, it's used to make pulses in lasers because pulses are short in time, so they are high in intensity. So you can say that locking modes of laser to get ultra short pulses is a similar problem to what we are addressing in the time domain, and we're doing it in the space domain. So it's a similar idea. And actually, there are papers showing a nice connection between them, some of them from Baruch Fisher in the Technion, which I highly recommend. So he did a lot of this temporal mode locking using similar concepts that I'm describing here. So let's do the following. Let's put the Sator absorber. First, it will reduce the duration of the pulse. Instead of getting hundreds of microseconds, we get tens of nanoseconds. And this we see, that's no. But because of this position, maybe it will act as a virtual pinhole in the sense that the minimal loss solution of the system now, including the nonlinearity, will be the phase locking. All the lasers in phase will give this sharp spot. The sharp spot will have high intensity, will drill a temporal hole into the Sator absorber, and will minimize the loss. This was the idea. We tried it, and amazingly, it actually worked. So no pinhole, and this nonlinearity actually gets you this phase locking, and though you can see it's not as good as before, for reasons which I can answer if I'm asked. So we were very happy, and we ran it several more times, actually about 500,000 times, just because we can. And what we found that about half the cases we got this, which is what we wanted, but the other cases we got this. Why? Because this, if you look here, here you have one sharp point, the in phase, and then the higher order diffraction. These are the 0 pi solution. And depending on the exact nonlinear function of this plastic, which we actually don't know, but in a reasonable assumption of whatever nonlinearity, you can show that these two have just about the same loss. So degenerate. And we already know that if the system has degenerate loss, it has degenerate solution, it would choose the solution with about equal probability. Okay, so we expected that, but the laser was a little bit more clever and thought of this solution, which we sort of forgot to consider, and we were only right half the cases. But then we saw this huge surprise, which I want to share with you. Before, when I showed you the degenerate solutions, for example, for the triangular lattice, they appear together. And I told you the reason they appear together was that each one of our lasers has about 1,000 frequency. I think that's different than your polaritons. So we have 1,000 lasers. Each one has 1,000 frequency. We actually have 1,000 experiments, an ensemble of 1,000 experiments, each one containing 1,000 lasers. I hope I'm not confusing you too much. And the system sort of shows us the result of these sum of intensity of the far fields. And this is why we usually get all the solutions at the same time. This was for the triangle and also for the Kagome, where I showed you these peaks. This was like average over the experiments. Here, what we show that either we get this one in some of the shots or this one, we never get a mixture. We did a control experiment, which I'm not showing you, where we used the degeneracy between in-phase and out-of-phase solution. It's again one of these Talbot distances, but with linear coupling, not with the nonlinear. And what we got is a far field composed of both of the solution at the same time because of the longitudinal mode. So the surprise here is not just that we have these two solutions, but all the solvers. Let's say that each one of the frequency represents a solver composed of 1,000 lasers, and the solution would be in phase or out of phase, and they're just about degenerate. So all our solvers have to find the same solution. The reason, by the way, is I can explain it twice. First, clearly, a mixture between these two will not be a minimal loss solution because of the nonlinearity. So in a nonlinear system, the superposition of two solutions is not a solution. You see, here I have few spots, here I have few spots. If I have all these spots, the power is distributed between more spots. The intensity of each spot is smaller. And because of the nonlinearity, the transmission of the SLM, of the Sator absorber, is less good. So this is one way to understand why choosing a superposition of the two solutions is bad. Alternatively, you should remember that the Sator absorber has some response function which actually can couple us in the time domain, as we know, because it does coupling between longitudinal modes. So it actually couples between the solvers. Okay? So nonlinearity provides us not with many solvers which are now forced to find the same solution. And this is a very clean fact. No one of these 500,000 tries gave us the degenerate solution. Is it good or bad? So it turns out this is actually a good property. If you take many solvers, if I ask you now questions, and you don't console with each other, I'll get solutions. And if the question has two almost degenerate solutions, I will probably get half solutions for each. But if I allow you now to discuss among yourself until you reach a consensus and you come to me with one answer, this is going to be a better answer. Of course, for exact degeneracy, there's no meaning. So what we did next, we broke the degeneracy between these solutions by a tiny amount. So now one of them is better. But the single solver, it's hard for it to solve it because it has noise and finite resolution. So the success probability for a single solver is, let's say, only a little bit more than half because they're almost degenerate, only 51%. But now if I have 1,000 solvers and each one has 51% for success and they interact with each other, the probability for success goes up tremendously. Okay, so coupled solvers is actually a good idea, and there's a little bit of theoretical literature about that, in people that do solvers. And we did experiments. So the horizontal axis here, we change a parameter which breaks the degeneracy between the two solutions, where they cross exactly here. This is a 50% success rate. It's where they're exactly degenerate. And when we break the degeneracy on the right, you see the nonlinear coupled solvers. And on the left, you see the same solvers, but now only with linear coupling. So we remove the satural absorber, and you see that this sharpness, how much you have to break the degeneracy so they are now perfectly finding the correct solution, is about 20 times better. So coupled solvers know how much better to distinguish between near degenerate solutions, as we demonstrate here. As I told you, when we tried to dig 1,000 holes, at some point we got sick of that. And what we did, we took a spatial light modulator, which is a device that can control million pixels. And in particular, it can make any mask you want just by programming. And this is just an example where we decided now we want quasi-crystal, now we could make it. And when we phase lock a quasi-crystal, you get these nice 10 diffraction peaks. Not very deep, but it's sort of a nice result. And we could play many, many games with this spatial light modulator. It's a bit expensive device. It costs about $20,000 from either Hamamatsu or Holei, and it actually burns quite often because inside the cavity there's a lot of field and spikes. So this is a bit painful for us because we have to buy a new one every now and then. And to justify this, we actually make the spatial light modulator work even harder for us. So now it will not only act as an amplitude mask to select the array of the laser, but it can also act as a phase mask because it can do that. And then we said, why don't we do adaptive optics, where we'll try to perfect our system by controlling each one of these pixels, the phase of each one of these pixels, because changing the phase of the pixel changes the effective length of the cavity, which changes the frequency of the laser. And as you know, that only lasers with identical frequency are phase locking the best. So by doing that and making some iterative algorithm, which we didn't publish yet, this is where we start from. Just to make the point, we reduce the strength of the coupling. So now the coupling strength is about 10 times weaker than what I showed you before. And when you look here, you can see that the lasers are not phase locked very well. But after the adaptive optics with the same weak coupling, you see these very nice diffraction peaks. So that means that our system now is much more perfect, even after the best alignment that our best student could do. We actually had a competition between all the students and the SLM, and the SLM won by about a factor of 6 in uniformity that we can deduce by the size of these peaks. And the amount of uniformity that we have now is on the order of lambda divided by 500. So that's not bad for a system, that is built in academia, not by good engineers. All due to this spatial light modulator, which has these, 1024 degrees of freedom. So what do you do after you correct to perfection, lambda over 500? Of course, you spoil. So we could, now that's the third test that we gave to the SLM. Now we wrote a random phase distribution on it because we're interested in the effect of noise, but in a controlled way. So each pixel has a different phase, and this would, of course, spoil the coherence between the laser. And if you think about this Kuramoto model, you have now this random distribution of frequencies for each laser. Or in the language of the XY magnetic field, if this was the XY Hamiltonian, we add to each XY spin, which is rotating in the plane, we add a vertical magnetic field, which is now not uniform. If it's uniform, you just take it out, and you go to a rotating frame. And what will happen is we increase more and more the noise, we put some distribution, we try Gaussian, we try uniform, with some RMS. And you see when there's no RMS, when it's 0 or lambda over 500, we get perfect phase locking, sharp diffraction peak. And as we get more and more, and you see this is only pi over 10, so it's only 1 over 20 of the wavelengths, it's already enough to spoil phase locking considerably. And if we do, lambda over 10, this is lambda over 20, lambda over 10 RMS, you almost get no phase locking. And when you quantify this by measuring the width of the peaks, for example, the width or the inverse participation here, as a function of the RMS of this order, you see this decay. And this is done for nearest neighbor coupling. We repeated these measurements for the long-range coupling with the pinhole in the far field, and we got this different result, which quite agrees well with the theory. And the theory tells you that you should get crossover for nearest neighbor coupling as a function of this order. It's not Kosterlitz-Towless, as some of you might think, because Kosterlitz-Towless does temperature, and this is quench disorder, but there is a bit of a relation between them. And you should get a second-order phase transition for the Kuramoto model long-range order. Okay? And of course, we cannot say that we see second-order phase transition. We're still not there, but we see at least a qualitative difference between nearest neighbor and long range, illustrating the importance of the range of the coupling. And this actually was studied by many clever people, Strogatz, Arechi, Kuramoto himself, but we were sort of interested by what Arechi published. And Arechi is a famous physicist, I'm sure some of you know him, and he showed these figures. This is like the coherence as a function of disorder, and you see these reduction, discontinuous derivatives of second-order phase transition, and then you see this point, which rows are curiosity. So this, here you have a jump, or something strange, discontinuous, which is more like a first-order transition. Why? So when you look into Arechi, you understand the answer, and the answer comes from breakdown of the mapping to the XY. So the XY would give you second order, but the coupled laser, when the mapping is not exact, for example, when the intensities are not the same, you can get this first order transition, and we were curious. We were also motivated by this funny story about the Millennium Bridge in London, which I think it's close to you, so many of you have heard about it. It's this nice bridge that was built towards the Millennium for pedestrians, and it was a good bridge, except when people started to walk on it, and when the number of people crossed some threshold, I'll show you just. It started to wobble in a very annoying way. So they had to close it down and to fix it. But they had 3 months where they took some crazy physicists that actually did experiments with people, and they put more and more people on the bridge, and they saw something that, as far as you can do with people, looks like a phase transition. So when the number of people exceeded a certain number, the bridge started to wobble, and this is published in this very nice paper by Strogatz and Ott and others. And we wanted to do a laser simulator of this phenomena, which is also called crowd synchrony, like neurons in your brain. So what you change is now the number of participants. And of course, you understand that the phenomena has to do with the people moving the bridge just a little bit. And then the bridge sort of mediate this movement to other people. And when you are walking on a moving bridge, you're synchronized to the bridge. So the people interaction between the people will be mediated by the bridge. And what we did is we built a composite laser setup. The first part is what you already know. Is the horizontal one is the degenerate cavity. And we have a mask with holes. Each hole is a laser, which is 1 people walking on the bridge. And they are not coupled at all. However, we have now this branch, and the branch here that we call the laser has this small aperture in the far field, means that the laser is coupled to all the people. So the people are not coupled, but via the laser, you can think of the light. Instead of doing this, they go here, come back, go here. So the laser coupled between them. And we can control the parameters of this system very well. And what we decided to do is to change the number of people motivated by this crowd synchrony phenomena, and nothing else. So here's the experiment. We took 42 lasers or 45 lasers. Now with the spatial light modulator, it's very easy to decide how many holes we have. And we looked on the synchronization. And these are the 2 far fields. For 42, you have this broad distribution, maybe a little peak here, so almost no phase locking. And when you increase the laser just by a little bit, you get this perfect phase locking. We were amazed to see this sharp transition, and we quantified it. Again, this vertical scale corresponds to the sharpness of the peak, and this is the number of lasers, and you see this sharp just about 43. Okay, so this is a well-controlled system, and of course with the people, nobody got this nice result. We repeated it actually many, many times with different coupling, this first order transition. By the way, the first order transition has to do with the lasing transition of this laser bridge. So in order to get first order transition, you have to put the coupling laser just below threshold. And then, as you could imagine, by becoming synchronized, now it will get a signal from all the other lasers, the pedestrian in phase, which will allow you to cross threshold, which will make the oscillation much stronger. And this is a jump. Okay, so the nonlinearity of the system is what provides the jump. It also changed the critical exponent, actually. So on the bridge, the critical exponent, so we repeated it many times for different coupling strengths that we could control. And we measured this critical number, which we call MC. So you see each one of these points is actually a new measurement. And we did it for different type of lattices, a random lattice and a square lattice of lasers. And all these results collapse on this universal curve with this exponential critical exponent 2.4. which actually was calculated by Raj Roy, theoretically, and differs from the critical exponent of -1 for the bridge. So, and it's uniform, and it's a universal. So it's a nice system to study, not so practical, but nice. I was going to tell you quite a lot about non-Hermitian physics, but I think I'm really going out of time, so I want to skip that part. If you come to Hydra next month, I promise to start with that. So I have to skip all that part. Yeah, sorry for that. I'm also going to skip topology, regretfully, which is another interesting picture. And I just want to give you a taste on this continuous problem. So I'll just show you one of them. Now we don't have spins. So we just remove this mask, and we have this continuous field that we control with the intracavity spatial light modulator. And we look for problems. And we have like 4 or 5 problems that we solve, and I'll just show you one, which I think is a bit surprising. So the problem we want to solve is called the inverse phase problem. What is the inverse phase problem? You have a field, amplitude and phase, and it diffracts. And then you get the Fourier transform. But you only measure the intensity of the Fourier transform. Why? For example, in X-ray, you don't know how to measure the phase. In optics, sometimes you're just lazy. Okay? So you know the intensity of the Fourier transform, and what you want to know is the original field. If you had the intensity and the phase, of course, you'll only do inverse Fourier, and you would find it immediately. But because the phase is missing, you have to guess it or to find it. And this is called the inverse phase problem, and it has many, many, many applications. So it's like books and books and libraries written on it. And there's no general solution. And in particular, it doesn't always converge. In the general case, it has a complex landscape with all these local minima that I showed you. It actually could even be NP-hard in some cases, although not always. And we were interested in that problem, and we asked, can the laser solve it? And I want to remind you, the laser doesn't know about problems. The laser only knows how to minimal loss. So if you want to solve a problem, you have to formalize it such that the solution will be the minimal loss solution for the laser. Okay? So what did we do? We did 2 things. The first thing we did is write here on the spatial light modulator the intensity that was given to us, by ourselves, but we didn't cheat. So we just took the intensity of the Fourier transform and we put it here on the SLM. And now we know that the field inside has this intensity here in this plane. Okay? And the object that makes it supposed to be here in the Fourier plane. And if we are able to write the correct phases, which is what we did so far, then we will get the right object. Okay? But how will the laser find the correct phases, which of course is free to do, because in the degenerate cavity, the phases is this free degree of freedom. It has to be the minimal loss solution. So we looked into this phase retrieval business, and it turns out that one of the common assumptions about the object, you need to make assumptions on the object, sparsity, separability, but one of the common assumptions is called compact support. What is compact support? It means that the object is finite only at a certain area, and outside of it, it's either 0 or exponentially small. Maybe you know this area because you measured it with a low resolution optical microscope or so, or maybe you just guess it and iterate. So if we know what is the external shape of the object, in this particular case, we knew that it's a circle, we'll just put an aperture here in the Fourier that limits to the external size. So for the correct phases, we will get the correct object, which fulfills the compact support assumption. But if the phases are incorrect, light will be diffracted outside of this region, and will cause loss. So by imposing this loss mechanism and the compact support assumption, the minimal loss solution should be the correct solution. Okay? With an external shape which we determine. So don't look on the external shape. This is not like the bit. So this is what our laser found. This is the field that formed inside the laser, and this is the shape that we introduced. So you see it's not perfect, but it's not bad. And we did it several more times. We give the diffraction pattern, we put a circle, we get this, and we compare it to what we get, and we did it again and again, and it works not well. We have actually lots and lots of graphs benchmarking this solver, because let me tell you a secret. This is now 2009, and 2009 is already a little bit too cute for the referees of Science Advanced to say, you know, why, this is cute, let's publish it. They want to see benchmarking, they want to see scaling. So now our field is a little bit more mature, and we have to like show that things really work, or at least scale properly, as we found out in the hard way. So we have to really map this configuration space. But even if you could sort of say, okay, this is not the best solver I've seen better solvers, and I've seen them as well, this is definitely the fastest one. So this was done, all this solution is achieved in less than 100 nanoseconds, and this is at least 1 million times faster than it would take, you know, not a network, but our little cluster here on Weizmann to find this ground state. So we have it sort of a quick and dirty approach. We don't find the best solution, but we definitely find a very, very fast solution. And in terms of complexity, this is not so bad. Okay? I'm going to skip other few problems. I cannot resist to show this, even though I'm really, really late. So this is real life problem. You know, you are living in Gotham City and there's something bad happening. You have to shine this laser beam on the sky, so the hero will come to save you. So you have to do beam shaping, as in the movie, if you've seen. The problem is that sometimes you need Superman, and sometimes you need Batman, right? And so you need some kind of a beam that will be Superman in one position and Batman in another position. So how does our laser solve this problem? So it's very easy. All you have to do is to tell him, in this here, you put a mask of Superman, and he will have to adjust. By the way, he has to fill the mask. And the reason he has to fill the mask because of entropy. Okay, so actually, I cheated you a little bit all the lecture, and I told you that the laser minimizes loss, and loss maps to energy because of this I, but actually he has to minimize this free energy. So he minimizes loss, or this complex energy, under the condition of maximizing entropy. And here it translates into filling the mask and not making like a very tiny hole in the middle, which would have too small entropy. And if I put in another position in the cavity, a mask of what's the other hero, of Batman, and I just take a picture of the beam as it propagates inside the laser cavity, this is what I see. Okay, so which of course, I'm sure you could do yourself with some Gershwin Saxton, because you just have to require these two things, and there are phases that fulfill it, but our lasers know to find. And if you have another hero that you want, just tell me, and or send me the mask, and I'll make it as well. So with this sort of amusing example, I want to finish, and just to remind you that I mainly talk about spin simulators. I showed you all sorts of cases of spins, the easy ones, the complicated ones, and the, I don't know how to call them, quasi ones. I didn't have time to talk on topology, unfortunately, so I cannot tell you about Kibble-Zurek and open rings and closed rings. I showed you these jumps that are sometimes first order rather than second order due to this strong nonlinearity of the systems. And I just glimpsed on how to solve the inverse phase reconstruction. And another problem that we solve is how to image pictures through scattering media, which is another important problem in real life if you want to go to a surgery. And again, we found a way to translate it into some kind of a minimal loss solution, and that enabled our laser to solve it. Again, not in the best way, but again, about 10 to the 6, 10 to the 8 times faster than any other method that exists. So again, quick and dirty, which is sort of nice, because in this business, everybody asks you, what is the probability to find the absolute ground state, which is sometimes, you know, a bit annoying. So I want to thank you for your attention, and you can call all these things complex light laser, which we just published an easy to read paper, actually too easy to read, in Optics News 2 months ago. Okay, and really sorry for speaking for so long.
Nir, thank you very much for this very exciting talk today. You really stimulate our work here in the field of polaritonics. So I guess this is the team that has really done the work, yes?
The green ones are now here. The red ones have unfortunately left, so we need to take a new picture soon. And all the other ones are the cold atom ones, which are great, but I didn't discuss them today. So it's about half.
So, Nir, thank you very much. Are there any questions? Please raise your hand and I will try to manage before we move on. So yes, so Sergey.
Thank you very much for interesting talk. My question is about aperiodic structures, which you demonstrated with tenfold symmetry. If I understood correctly, you used Gaussian mask there as well. And the question is the following: did you try to vary the coupling and see what happens with synchronization? How does the coupling affect whether you form this quasi-crystal or not?
Okay, so the question was about this quasi-crystal. So first, I'll answer first that this was not done with the Gaussian mask, and you can see it here because this is like the tenfold version of the out of phase coupling. So if it was in phase, it would be a little bit more boring. We would just have this point in the center. And this already raises the question because it's out of phase, you have a little bit of frustration and a bit of interesting algebra. So we actually had some discussions with the theorist of quasi-crystal from Tel Aviv University, Ron Lifshitz, and he gave us a list of interesting things that should happen. And I have the list in my, on my table, but we didn't reach even item number 1. So this is sort of unpublished result. But if you have ideas and suggestions, of course, you know, if you use the analogy, I like the analogy with spins, but this theorist actually worked on nanomechanical oscillators sitting on these quasi-crystal lattices. So there are a bunch of effects there which people are interested in, but we haven't demonstrated anything yet. If you have an interesting idea, I'd be very, very glad to hear, but I don't promise to do it soon. We are sort of now busy with this spin glass thing and with the topology.
Thank you.
Okay. Thank you.
And that's why it's published, because there's really nothing very interesting about this result.
Okay. Tamsin has a question. Tamsin, please.
Hello, thank you for the great talk. I was wondering, you made a comment at the beginning that the Ising spin model had many advantages over the XY. Could you comment at all on what these advantages are? Yes,
but you know, many. I will translate many into 3, and I think I'm not probably the best person to ask. So I can ask, for example, Natalia Berloff in Cambridge. She knows much better than me, or Toby Cubitt in Oxford. But for my poor knowledge, I'll say 3 things. So as an experimentalist, I envy the people that work on Ising because they only have to read whether the phase is up or down. And when we published this paper about the small deviations because of the non-uniform intensities, we ended up measuring the phase with about 20 degrees accuracy, which is terrible. And the error bars are terrible, and the referees are unhappy. And it was not so easy because the system is not perfectly stable. So this is already, I said it as partly as a joke, but you can see that it translates to the advantage of a digital system. So a binary digital system with plus and minus with only 2 values is more robust to noises, not in all senses. So in the readout sense, it's definitely robust. You could ask, for example, what happens if I write the wrong Hamiltonian? I make a mistake in the connectivity matrix. Will the Ising Hamiltonian be more robust? Will the solution change less than for the XY? The answer is probably not. So fundamentally, it's not a fundamental difference, but it's very convenient. The other advantage, which is, of course, the advantages are related. So the other advantage, maybe because of that many more people worked on the Ising mapping. So if you open like the books on mappings, there are these thick books for the Ising and the rather thin one for the XY. And this is important because it's, you know, like comparing Mac to PC. You know, who writes the application? important aspect, even though it's not fundamental, but it's related to these fundamental issues. And the third one is, of course, physicists know many interesting differences between X, Y, and Ising. What is the critical dimension? It's 2 and 4, respectively. And, so dimensionality plays an important issue. And complexity translates, for example, if you take the Ising on nearest neighbor random coupling with external fields, it's already can be mapped to an anti-hard problem. In the XY, you have to avoid these sort of planar gaps. You have to go to one higher dimension to get complexity, which is, again, not fundamental. So, and then there are some other differences, but maybe it's a good time to stop. So I think I get the flavor. It's not fundamentally different, but practically there are quite a lot of practical advantages for the Ising, by the way, which also makes us build now a spatial Ising machine using an array of DOPOs, degenerate OPOs, but it's actually, if I have to balance, it's much easier to build an array of lasers, an array of DOPOs. We have the gain of our laser system. We have 1,000 lasers, and the gain of each laser is more than 10. Whereas for OPOs, if we take 10 OPOs, we get a gain of 50%, which means that anything to do in the cavity has to be less than 50% loss. So I'm thinking about a minimal loss solution, but in many cases, the minimal loss is not zero. And you need enough gain to compensate for that. So it's not so easy to build an all-optical Ising machine. What Yamamoto does is, of course, not all-optical. There are a lot of discussions, with good, bad, but all-optical system containing, say, 1,000 Ising spins was not yet built and will probably not be built in the near future. So that's why I can, live for a while.
Thank you. The other question I had was, in your masks that you drilled holes. Did you ever drill different shapes, like with the laser drill, triangles or squares or lines, or?
For each laser, you mean? For each one of the holes, what is the shape of each one of the holes? So the answer is not an yes. We didn't drill them, but now we don't need to. Now we have the spatial light modulator, and this is like a super mask, which is extremely programmable, which, as I illustrated twice, I can make any hole geometry. I showed you, this tenfold and square and Kagome and whatever, and we can change them, from shot to shot. And of course, we can change the shape and the geometry of each one of the holes. We never went into things like triangles or that, but we definitely looked into the size of each hole, and I don't want to abuse the fact that you asked, but let me just say that the smaller the holes are, the more correct is the assumption that each one of the lasers is a single Gaussian mode. And actually, we found that if you open the holes a little bit and allow a little bit of internal structure in each one of the lasers, and I think polaritonics have a very good analogy, because some of these polariton systems actually have internal modes between them, and then you ask yourself, how does these internal modes compete? You can code, by the way, you can code Ising spins with these internal structures, so this is another promising advantage. It doesn't have to be with 0-pi phase. There are other mappings. And also, we actually published one very nice result where we could identify a stripe phase. Stripe phase is a term that we borrowed from the high-TC superconductors in the Kagome lattice when we introduced a little bit of internal structure. So I absolutely agree that it's an interesting degree of freedom, and if anyone here has a concrete idea, what to do with it, I'd be more than happy. But the short answer is we could do anything now. So just give me a hole shape, whatever you want, and we'll do it. And with this superb, we all know SLMs. They are just like an amazing invention. We have 2 million pixels in our disposal. Whatever dream we have 2 million pixels to implement it. And just once in a while.
Thank you very much. My last question was, if you have time next week or in the coming weeks, I would be very interested in the topology and Kibble-Zurich part of your talk, if you ever have time to discuss it.
Oh, absolutely. So let's just write him an email, and that goes for everyone else. Well, we all know that we like to talk on what we do and to discuss and to learn from other people. So absolutely, yeah, with pleasure.
So,
thank you.
Yes. So the next question is from Tilo. Tilo.
So thank you very much, Nir. Very inspiring talks. I have a question about the role of noise, because lasers can have also a lot of noise. How does this influence the solution? Does it influence the quality or the convergence?
Okay, this is an excellent talk, not in the sense that I know how to answer it well, I don't. So I would say that in the talk, you show all the things that worked well in your research, and in the discussion after, you come into all the things that didn't work so well. So the two things that we are really lagging behind is quantitative study of noise, not the quench disorder. The quench disorder, I think we did very well. We really understand it really perfectly, but that's, of course, a very specific type of noise. It's like a DC noise of the laser. And I guess what you were referring is other types of noises, like, let's say white noise or fast noise. And we know they're there. We know they exist. We cannot zero them so nicely like we did with the quench disorder. We could, to some extent, we could add them, and we did that. We just injected more noise into the system, and we saw deterioration. But because we don't start with a perfect system and because we don't control the noise, we don't have quantitative analysis of that. For example, we were very much interested to inject temperature-like noise. And I don't want to discuss here, but my theory friends explained to me, when does the noise behave like temperature in terms of renormalization group and these kind of things. So we know what to do, and I would very much like to do it and to observe the Kosterlitz-Strauss phase transition that I should. And I think this would be a really nice thing to do. We tried it actually twice and it never worked. So I think we are still not doing well in terms of controlling the noise and understanding it on a quantitative level, which is needed to observe phase transition. We did advance to some extent. When I show you the pictures, this was an old laser system, and now we went into like a more modern, it was a lamp pump, now we go to a diode pump, now we went to a third generation of an even quieter laser, and we clearly observed that the quieter our system, the better our solutions become. And in what sense, does it take longer to reach a solution? If we could control the noise, maybe we could do some annealing. Let me still have one more comment. Even though the real noise is something we don't control well, there is an additional effect, which is called relaxation oscillation in lasers of this type. And this actually acts as an effective noise that we can control very well. So it's not noise, it's just these rapid oscillations that exist when you turn on the laser, but when you can consider them almost as noise because they are not synchronized with the phase dynamic. And actually we have a paper, it's this Kibel-Zurek paper. We actually have two papers where we use this, let's call it controlled effective noise from the intensity as an annealer. And we show that when you put the lasers on the ring, there's of course these discrete vortices which are metastable state, and the system has a high probability to get stuck in them and not to find the ground state. And we saw that by introducing this strong effective noise and reducing it slowly, like an annealer should, we actually improve significantly the probability of the system to reach the ground state. So it's not what you ask, it's not real noise, but it just illustrates that noise is an interesting creature in spoiling and sometimes also in helping your solver to work.
Thank you very much.
And of course, we can always use noise as a fit parameter. And in the example I showed you about the nonlinear solver and showing that the nonlinear solver solved the problem, this near degenerate solutions better than the linear solver because of coupled solvers, there you show a finite slope. And this finite slope actually can tell you what the noise is. So we know quite well what the noise is, but it's not something that we introduce or control. So, so to some extent, it's like not well controlled.
So, Nir, I think I will pose the last question because we are approaching 1.5 hours now, and it is an open question which you already triggered in your talk, and I think it will stimulate discussions for our upcoming conference in Hydra, which is about the transition from the classical XY to the quantum Hamiltonian. So you said that you have taken some steps. Can you give us a taste of how one would go from a classical to a quantum Hamiltonian using a system like yours? Okay, so I had several steps. Let me describe two of them. So the first one is to take a big step backwards and not get close to this quantumness, which, as probably you all know, was very controversial,
in the quantum claims that Yamamoto made, and this was, a lot of discussions and controversy. So our first reaction was, let's stay out of there. A second step that I can describe is only for 2 lasers. So we have, I didn't show a lot, but we have actually quite a lot of working on 2 laser systems, which you could ask, who cares? But we find that this is like the nuclei, and to really understand well 2 lasers is very helpful when we go to this big system. So maybe 1/3 of our papers are on 2 or 3 lasers, like on the building block. And in one of them, we actually studied the effect of quantum noise on synchronization. And the reason we did it only on 2 lasers was that because, as I already admitted, we actually have quite a lot of classical noise. So how can you study quantum noise in the presence of significant classical noise? And the answer is very simple. You just walk so close to threshold that the quantum noise dominates. So working only with 2 lasers, we had enough control of the system, so we could walk so close to the threshold, so the noise characteristics we could analyze going from Gaussian spectrum to Lorentzian spectrum and some other parameters. It's quantum noise. So quantum noise is not really quantum effect, right? It's just spontaneous emission, but it's as close as we got. And we were able to show quantitatively that the effect, how the quantum noise affects on synchronization. That was the closest that we ever got to incorporating quantum mechanics into our effects. Not to say that I don't think this is an extremely interesting problem. There are people, there's a lady in Mallorca, I'm sure you know her, that she studies synchronization in quantum systems. And there's sort of a continued path. She's also looking on noise correlation, which could be, of course, fully quantum, and then it's entanglement and squeezing, but could be, semi-quantum, and then just noise correlation. So it's definitely an interesting avenue, and I agree with you. It will be good to discuss it maybe in Hydra, but I don't think I have contributed a lot to that field yet.
Okay.
And I don't think this is like the best system. We have actually preliminary work on going to diode lasers, and as everybody knows here, diode lasers are sort of a quantum creature almost to begin with, as cheap as they are. So that probably would be a better platform to go quantum, and we didn't do it yet.
Okay, Nir, thank you very much. Thank you for joining us today in our Polaritonics seminar theory. And I would like to thank also all the people who joined us from across the world, as I see here. So I'm looking forward to seeing you in Hydra. And with that, I think we can close.
Yeah, thank you very much all. And again, sorry for you not seeing me and missing.
No problem at all. Thank you very much, everyone. Have a good day.
Bye, everyone.